Forces, very fundamental part of this class. They are responsible for accelerations. They tell us why. There's a lot of why. We answer in whys here. So, all right. So, when it comes to forces, there's always an object that we're in. When we analyze forces, we have a single object that we are paying attention to. There is your object and there is the environment. Okay, the environment can exert a force on the object. And when that happens, we call that an agent, something responsible for the force. So this really cool looking football player here is throwing the football. We would say, if we want to analyze the football, the object's the football and the arm of the person, or you can just say the person is the agent involved. Okay, this guy's getting knocked out here. His face is the object, and the agent is this hand. Bam, right? Now, forces are vectors because they have magnitude and they have direction. So we will be analyzing everything with vectors. All right. There's different types of forces we're going to work with. The vast majority of forces are contact forces, meaning you have to touch for the force to take place. And there are some long-range forces, forces that don't need contact for the force to occur. Now, in this class, there are only really two forces that we would ever consider to be long range, and we really only deal with one of them. Gravity is long range, and electromagnetism is long range. You pretty much will not hear anything about electromagnetism in this class. 120 is all about that. So basically, gravity is really the only long range force that we're going to work with here. This is a very important point. One of the things that we're going to do today, would wind blow in a plastic bag be a long range force? It would not, because the air is in contact with the bag, and that's why the force is being exerted. That's it. I mean, let me put it to you this way. We don't really deal with electromagnetism at all in this class, but that is a long range force. Gravity is a long range force. Everything else is not. That's it. So this is important because we're going to spend a lot of time today, and of course for future things, okay, where we have to analyze forces. And if something is not in contact with an object, it is not exerting a force on it. Simple as that. Okay? Simple as that. So, if it's not gravity, there must be contact for there to be a force. Now, you mentioned here earthquake. The earthquake is a difficult thing to talk about here because we are still working on particle model. So when you talk about an earthquake, it's difficult to pinpoint what the object is. So I would say that for something like an earthquake, that's a more complicated problem that we are not going to deal with, at least initially. Everything right now is particle model still, where I have to draw a lot of pictures of things here. Now, I don't know how much you were a fan earlier of drawing pictures out for your problems, but if you weren't much of a fan of it, I'm going to have to change your mind about that because it's a requirement to some extent to draw pictures for what we do here. So a lot of that is drawing vectors. You got to draw vectors. Well, I can't imagine. I mean, yeah, I don't know why you're not drawing a picture, but whatever. So anyway, we have to draw a lot of vectors. And the way a vector is drawn is it has a length and direction, as all vectors do. Okay? The force that is exerted on a particle will be drawn so that the particle is at the tail of the vector and the force is drawn away from it, okay, in the appropriate direction. It doesn't matter what the nature of the force is. It could be a push or a pull. We're not trying to draw a visual representation of what's happening. We're trying to simply illustrate how the vectors look on the object. Okay, so for example here, we have this person who is dragging along a box attached to a rope. We say the object is the box and the rope is the agent. We wouldn't call the person the agent because the person is not in contact with the box. The person is not the agent. The rope's the agent. Okay? And the box is being pulled to the right, so we would draw a dot for the box and an arrow that points to the right. Now, this is only one force here, so its length is arbitrary. But if you have more than one force, you're going to have to be mindful about their lengths. They need to be drawn to scale, if you can do that. This one is showing a push by a spring. Okay, the box is the object, the spring is the agent. We would draw out the force vector like this. The box is the point, and the force is to the right. Again, the tail of the vector rests on the box. Now, this was a pull, this one was a push. Doesn't matter. The way the force is applied is not important. There's only two things important: magnitude and direction. Okay. Here's the long-range force. It's just gravity. We're showing the box and the downward thing. Now, there's no contact here. It's okay for gravity. Okay. Now, here's a really cool aspect of forces, is that they obey something called superposition. Superposition is a very important concept in physics, and it says that, and this is not just for forces, by the way, this can be for a lot of things. If there are multiple things having an effect on an object, like, for example, forces, maybe it's like a series of ripples in water. Yeah, that's another example of that. If it's an electric field or a magnetic field, something like that. All these things obey superposition. And what that simply says is that if you have, and I'm going to state this just for in terms of forces right now, okay? If you have multiple forces that act on an object, they all act independently. Okay? Meaning that the application of one force will not change how the other forces are being applied. Okay? And because of that, you can create a vector sum of all the forces and produce a resultant vector. And the resultant vector, which a lot of times we just refer to as F net, like net force, F net, is a single vector that can represent what the effect on the object is. It's like all of these forces act as if they're a single force that is exerted on the object. That is basically what we mean by superposition. When you analyze forces, the first thing you do, like if it's this box here, we identify the box, we identify the agents, we state all the forces that are exerted on the box, we compute a vector sum of them all, and we get a net vector, net force vector. And that net force vector is demonstrating for us, or showing us, how all those forces act together to produce an effect on the object. So in this picture down here, we see that we have a force up and to the right and one down. Now the effect of doing this to the box, these two are combining together such that it's acting as if there's a single force going down and to the right. And so we can represent this system, it can be simplified into that one force. That's superposition. Okay. And that obviously makes our problems very easy. Because if superposition did not exist, then you all would have to take differential equations before you take this class. All right, question for you. The net force on an object points to the left. Two of the three forces are shown. Which is the missing third force? So I'm showing there's a force upward. There's a force to the right. The net force is purely to the left. So you're trying to imagine what third force can combine with the other two to produce a force that just purely points to the left. You do want to be thinking about components. C, huh? I think by popular demand, it's C. By popular demand. But it is C. Actually, it is C. All right. So what's going on here? Well, if the net force is to the left, that means we're going to have a third force with a y component that cancels out F1. Furthermore, it will have to have an x component that is longer than F2. And that's what you see for C. Now, the other ones can be ruled out. I mean, A and B just don't work at all, right? Because A and B are not getting rid of any vertical components. D could be right. It's just the wrong direction. For 3, the vertical components cancel out, and the horizontal components don't completely cancel out. There would be a small net vector to the left because it's a little bit longer. So any questions about this, though?
Can you explain the canceling out part again?
Yeah. So when I draw this third vector here, I can state what its components are, which are drawn lighter here. The downward component for vector 3 matches vector 1, so they cancel out. The horizontal component for vector 3 is longer than vector 2. So they don't completely cancel out. There's a small residual force that points to the left. And A, B, and D can't accomplish that. Only C can. Sounds good?
Yes, thank you.
All right. Fantastic. Okay. Gravity. Now, what I'm going to do is I'm going to give you a little tour, right, of all different forces we're going to work with. First one is gravity. Gravity always points straight down. It is the only long-range force we are effectively going to be working with in this class. The agent is the Earth, the entire Earth, okay? And unless you're told otherwise, you should always assume that gravity is at work in the problems, unless you're told otherwise. Or there's something about the problem that strongly suggests you don't include gravity, like you're not on Earth kind of thing, you know? So, notice the notation here, F sub G. I usually use a lowercase g. I'm not really fond of uppercase g's. I think they're ugly. I like the lowercase g. It's a little bit more elegant in my opinion. So I typically go with that. Sometimes you'll see notation of a W for weight. That's really bad. I would say that you should not do that. That's extremely bad. It's not weight. That's a different concept. I'm pretty sure your book doesn't do it. I'm pretty sure. But the thing is that I know a lot of you probably reference things online, and there is a lot of information online about, basic general physics. The downside to that is that we don't, unfortunately, have like a consistent set of notation across all education. So you might see some alternative notation and things like that, which is unfortunate. But you might see a W. And if you see a W, you should tell the person that they're a fool. How about that? Tell them they're a fool. All right, spring forces. These are a type of contact force, somewhat of a vague force, where it's also considered a restorative force, where when you try to affect the state of the object, the force acts to return the object to its original state. And a spring is a great example of that. Okay, there's a lot of other examples of spring forces, right? A person standing on a trampoline, the upward force is a spring force. I mean, if you want to be, I wouldn't say that. That's a bad thing to say, actually. So, but we'll label that sometimes with an FSP for spring. Later in the class, we are going to say more about this force. We don't do much with it at the moment here. So, okay. Tension. This is a big one. Tension is typically something that's exerted by a string or a rope or a wire. It usually happens at a point of contact, not a broad contact. Okay, so when you're trying to determine if tension exists on an object, it's because there's a point of contact where there's a force exerted, like they're showing the rope pulling the sled here. Okay. Now what's happening, ultimately, on a microscopic level, tension is really just a bunch of spring forces. Really, it's what it is that when you're pulling on the rope, you are stretching out the molecular bonds to some extent, and that provides the tension. We don't get in that kind of detail, but I just wanted to throw that out there just to make you say, that's interesting. Okay, okay. A steel beam hangs from a cable as a crane lifts the beam. What forces act on the beam? What do you think? What forces act on the beam? Steel beam hangs from a cable as a crane lifts the beam. What forces act on the beam? Okay. I see a lot of B's. I got some D's in here, though. B's and D's. Okay. Excellent. I'm very happy with your responses, even though some of you are wrong. I don't mind when they're wrong. I really don't mind at all. I love it when you're wrong. You know why? Because it's called a teaching moment. I can teach you something because you don't understand something. I'll explain it to you and then you'll know it. That's teaching. That's teaching right there. Okay. Is there gravity? Well, there better be because that's all the options we got here. Tension in the cable, you bet. Cable is in contact with the beam. There is absolutely tension. It points upward, right? So I like B a lot. D, however, gravity, tension, and the force of motion. Here's a problem with that statement. Remember, forces need agents, right? Gravity, what's the agent? Earth. Tension, what's the agent? Cable. Force of motion, what's the agent? You okay? Okay. Force of motion. What's the agent for that? Don't know. If you can't identify an agent for a force, it's probably not a force. No, the crane is not in contact with the steel beam, right? The crane is not in contact with the steel beam. The cable's in contact with the steel beam, not the crane. When I say in contact, I mean literally touching. It has to literally touch. Crane's not touching the beam. So it has to be B. Air resistance is a nasty phrase. Nasty. You don't consider air resistance unless it's indicated in the problem because it's so rare to do. So we would not consider air resistance here. So the crane lifting would just be on the table. What? Where's the table? I don't know where the table. What do you mean by table? So there's a beam. There's gravity down and tension up. The only thing that touches the beam is the cable. So there can only be two forces. Oh, okay. Okay. Yes. So the crane lifting would just be on the cable. Yeah, I mean, you could analyze the cable. What forces are exerted on the cable? 3. Gravity, the beam, the crane. That's what's going on with, I'll see, guys, we learned something. I'm doing my job, sort of. Let's keep going. I am. At least 2 people learned something. Normal forces. Normal forces are very similar. Oh, by the way, tensions, just FYI. Oh my gosh, I'm going the wrong way. Capital letter T, which looks like period. We only got so many letters, people. T is tension, and when it's in vector form, right? That's how you can tell the difference. Okay. Normal force. Now the word normal is like strange word, right? Normal, like a regular force? No, normal mathematically means perpendicular. That's the word normal. Okay, it does not mean normal. It means perpendicular to. A normal force is a broad contact force generally exerted by surfaces. Okay? So the book's sitting on the table. The table exerts a normal force on the book. Broad area of contact. There's a difference between tension and normal forces. Tensions are a point of contact. Normal forces are broad contact. The normal force is always perpendicular to the surface that's exerting the force. So like they're showing here, if you want to see on a microscopic scale, the book exerts a normal force on the table. The table force exerts a normal force back up. On a microscopic level, it's also like a spring force. But we're talking about forces on a macroscopic level. And so we would consider this a normal force. We get a lowercase n to indicate that. Lowercase n.
So does that mean gravity's a normal force because it always pushes down the same direction?
No, gravity's never a normal force. Never a normal force. What's happening here is if you analyze the book, gravity points down, normal force points up from the table. If you look at the table, there's a normal force that points down from the book. Gravity points down. And assuming that the table is not levitating, it's in contact with the ground, there's a normal force up from the ground. But yeah, normal force and gravity is different. And this is confusing to a lot of people because when you sit in your seat, right? I'm sitting in a seat, right? And I'm in an equilibrium. And what that means is gravity is trying to push me down, and the chair is exerting a normal force pushing up on me. Those forces are equal, and they're opposite. But that's due to equilibrium. And you don't want to say that gravity and normal forces are the same kind of force. I'm just expressing to you an equilibrium situation. Okay? I mean, I could hang, from those gym ropes at the gym, right? When you climb up gym ropes, I could hang from that thing. And it's the same thing. Tension's holding me up. Gravity is going down. But I wouldn't say that gravity's tension. I wouldn't say that. So, okay. Oh. All right, I think that's good. All right, so this person they look pretty angry at this wall. Now, when they push on the wall pushes back on them, and we would call that a normal force. In fact, there are two normal forces on this person, right? The ground and the wall. That's what's happening with this person, in addition to gravity, of course. We see a frog who is admiring this person trying to push on the wall. Quite happy, this frog. This frog is really happy. There's a normal force exerted on the frog. Okay, gravity points down. If I could draw that, I can show a gravity vector that points down. Okay, but the normal force points perpendicular to something like that. Okay. Now, if this frog doesn't move, there must be some kind of friction. Which probably goes like this. We haven't talked about friction yet. But anyway. Perpendicular to. Oh, here we go. Here's friction. This is good. All right. We have two types of friction we're going to be working with. Two types of friction. Kinetic, static. They're indicated, this one is a lowercase f, or like a cursive f with a subscript k. Kinetic friction is a force that opposes motion. An object must be moving for there to be kinetic friction. They're showing a child on a sled. The velocity is to the right. And if there's friction, it opposes the motion. It must point to the left then. Point to the left. If your object doesn't move, there cannot be kinetic friction. It's always opposite the direction of motion, and it acts to slow the object down. So if I were to tell you what's going on with this person here, this child with the sled, it would look like this. We have gravity pointing downward. I'm going to treat the sled child as the object altogether, because it gets dicey if you want to just think about the sled or the kid. It gets a little bit funky, which we're not doing funky right now. Gravity's down. Normal force is upward. Kinetic friction's back. And those are the forces that are exerted on the object. We would not include air resistance. We are objectifying people, yes. We are objectifying people for the benefit of physics. Don't worry, it's not a bad way. It's a good way. Okay.
You said normal force is up, right?
Normal force is upward, correct.
Okay.
Gravity's down, kinetic friction's to the left. No air resistance, because we're not told there's air resistance, so we don't have to include it. But you could. You put a little tiny air resistance vector going back like this. You could, but it's tricky. Mathematically, it's tricky. Air resistance is tricky mathematically. I'll just say that. Okay, there's kinetic friction. Okay. A bobsledder pushes her sled across horizontal snow to get it going, then jumps in. This sounds fun. After she jumps in, the sled gradually slows to a halt. What forces act on the sled just after she jumped in it? Ooh, this is a good one. This is a good one. What do you think? Let her in the chat. I dare you. I dare you to get this right. I got some rebels in here, but everybody else is pretty much C. Sounds good. It is C. Because again, force of the push. What's the agent there? What's the agent there? Bobsledder pushes her sled across horizontal snow, gets in, jumps in. Once you jump in, you're not pushing the sled anymore, right? So it's not that. It's not D. I mean, I just gave you the example here, gravity, normal force, kinetic friction. So you could say, well, maybe the force of the push. No. Are they actively pushing? No. Then there's no agent.
Is the object the kid or the bob? I mean, the sled.
The object would probably be considered the bobsledder plus sled. That's what we do it. Yeah. Matt, never use the word inertia again. Don't say inertia.
And with kinetic friction, that's always like the opposite of what the object is going.
Opposite of the velocity vector. Yeah. All right. Static friction. Static friction occurs between an object and a surface. Okay? Static friction is a type of friction that opposes the start of motion. Opposes the start of motion. And it points opposite the direction of what motion would be. Opposite the direction of what motion would be. When it comes to static friction, there are two things you need to keep in mind, because static friction is easily the hardest force. It's conceptually a little more challenging. Here's two things to remember for static friction. Static friction can only occur between an object and a surface when the object and the surface are not moving relative to each other. Can it happen with objects that move? Yes. Static friction can occur on objects that move. The question becomes this: is the object moving relative to the surface that it's in contact with? Okay, if it's not moving relative to the surface in contact with, there's static friction involved. And the second thing you want to remember is ask yourself this question: if there wasn't static friction, which direction would it go? And then you choose the opposite direction. The frog here. The frog, if there's no friction, would slide down the incline. Okay? Currently, they're not moving relative to the incline. So there is static friction. And if they would slide down the incline, then static friction must be pointing up the incline to prevent the motion. Okay. Now, while that may sound simple to you, it can be a little bit difficult. For example, let's go back for a minute here. What time we got? We good on time? Oh my goodness, we're so good on time. Let's go back to this. And I kept telling you, like, let's just make the kid and the sled a single thing. Let's just make it a single thing. Because it gets complicated if you do that. All right. So, guess what? What is going on with the kid? Right? What's going on with the kid here? Let's just look at the kid, not the sled. There is a is this? Where's my arrows? Please. Just give me my arrows. Okay, gravity downward. Exerted by the Earth. Normal force upward. Static friction. Which way? Up, down, left, right.
Right.
Oh, who said that?
I did.
Michael. Is right. To the right. Why? Because if there were no static friction, what would happen to the child? They'd fall off the back of the sled. So there must be static friction propelling them forward. Yeah.
So there's static friction on the sled?
There was static friction on the sled. If the sled is exerting a static frictional force on the kid, and according to Newton's third law, which we'll get to later, there is a static frictional force exerted on the sled too. Anyway, I'm jumping ahead of myself a little bit. Hopefully that discussion was intriguing. It's like, can't wait to study that later on. All right, now, very infrequently, but we do talk about air resistance, or what we call drag. It's indicated with a capital letter D, and it is basically the same as a kinetic. It's a resistive force. It acts pretty much the same way that kinetic friction would act. These leaves are falling down due to gravity. There's an upward drag force that causes them to slow down. They're in contact with the air. The air is the agent. Okay. Now, we're generally going to neglect air resistance in our problems unless we're specifically told to include it. And the reason why that is because for most drag problems, because mathematically, air resistance is not simple. It requires a differential equation to properly analyze it. So, thrust. Very rare that we encounter this one, but thrust is a contact force. You are expelling gases out the back, and by pushing gases out the back, you're pushing yourself forward. So we usually indicate that with an F thrust. We don't deal with this too much because it's also complicated. Thus the rocket scientist jokes. It's not that complicated, to be honest, but not a 110 level topic, put it that way. Okay. Electricity and magnetism is all for 120. It is a long-range force. To my knowledge, I think there's like one time in this entire class where I will mention this. So I don't have much to say about it right now. Okay. Again,
was that comb attracting the water in that picture?
Yes.
Strange.
Yeah. Well, what's happening here is, you rub this comb enough on, hair or say wool or something like that. Like if you rub it on wool, you're going to be ripping off a lot of molecular ions. And if you build up enough of that stuff, yeah, water's polar and water will deflect. But what you can't tell here is that this is, if you chemists in here can help me out. I don't remember the name of this thing, but it's a pretty thin stream. It's not easy to deflect the water, but yeah, let's do some examples. Now, we are going to go through this very carefully. Do you remember when we solved our kinematic problems, right? I had a method. Okay. And that method was what I called the pictorial representation, right? Where if you really wanted to put a lot of effort into solving your problem, to give you the most comprehensive treatment of it, I had you draw a picture, maybe a motion diagram, identify variables, and so on. And do you have to do a pictorial representation every time you do your problems? Not necessarily. If you think the problem is simple enough and you can properly explain it and get the answer right, then you don't have to go that extra mile with that. But it's something that you should do if you find the problems to be challenging. Okay. So Now, the first part of analyzing these problems involves something called a force identification diagram. And I strongly recommend you do this for the first few problems that you work on. In fact, the homework that is posted that you'll have for this lecture contains a series of scenarios where I'm going to ask you to do a force identification in addition to other things. So I am requiring it initially. Okay, now what you do in force identifications is you have to draw a picture of your object and its environment, just enough to see what's interacting with it. Okay, now, chandelier. It's my best attempt at the chandelier. I'm sorry. I draw a circle around the chandelier. It is the object. What is in contact with the chandelier? Only the chain. So what you do is once you draw the circle around your object, you can draw forces to indicate the direction of things. Now, gravity's long range. There's nothing in contact, so it points down. There is a chain that holds the chandelier, and so there's tension that points upward. Okay, a chandelier that hangs is in equilibrium. There wouldn't be any other forces. Okay, so that would be the force identification for that object there. Baseball player slide into home plate. So the object is the baseball player, which I've drawn. Again, don't even. I draw a circle around that person, and the only thing they're in contact with would be the ground. So I have the ground drawn here. Now I'm showing a velocity vector. When you have motion in your problem, you should indicate somewhere the direction of motion, because it helps to communicate if you've got friction correctly. Because by itself, it's not clear. I mean, this person's probably sliding to the right, but again, you know, you got drawing skills like me, it's never really clear. So if your area is motion, you should indicate the direction of motion. Okay. Anyway, gravity down, normal force upward, kinetic friction to the left. Now this is interesting because the agent, the ground, exerted two forces on the person. Normal force upward, kinetic friction back. Now that's okay, generally speaking, and I will say this, generally speaking, this is 99.9% of the time true. An agent can only exist, no, let me try that again. An agent can only exert a single force in a given direction. It can exert more than one force, but it cannot be in the same direction as another force. So in this situation here, we have a force exerted upward and a force exerted to the left. That's fine. That's cool. Car is parked on a steep hill. Okay, I draw an incline. I drew a car. Again, don't say a thing. Gravity's downward. Normal force is at that angle because of the slope, and there's static friction pointing upward because the car would slide downward. But this is the correct directions for things. So again, when it comes to force identifications, you're drawing an object, you're drawing the agents, you circle the object, and anything that touches the circle is in contact with the object, and you should include a force for that. That's how we do force identifications. Okay. Any questions about that?
Would that always be a force, gravity?
Unless you're told otherwise, always assume there's gravity.
When you're underwater, there's gravity still pushing you down.
Yes, but there's a lot of other forces. And so generally when you are, say, underwater, you definitely still have gravity. It's not as obvious because there are buoyant forces at work. So if you, for example, you know, if you put yourself underwater and then you exhale enough air, you can make it so that your average density matches that of water, and you sort of just suspended in the water. But that's happening because gravity is down and the buoyant force, which is dependent on your density, is upward. So yeah. So, I mean, you technically would say there's gravity, but some people, you know, not talking in terms of physics. I mean, some people kind of misspeak slightly by saying there's no gravity in water. Well, I mean, gravity's canceled out, but it doesn't mean it's not there, you know, so. Question for you. A ball rolls down an incline and off a horizontal ramp. If you ignore air existence, what force or forces act on the ball as it moves through the air, leaving the horizontal ramp? Letter in the chat. Let me know what you think. A whole lot of A. Oh my goodness. A lot of A's. Boy, you're making me very happy today. I'm very happy by that because you know why? When I normally ask this question, I don't get a lot of A's. I get a lot of other things. But here's the thing. Once the ball leaves the ramp, you ask yourself, what's in contact with the ball? Nothing. Nothing's in contact with the ball. I remember, we're ignoring air resistance. So there can only be gravity that acts on the ball. That's it. Because again, if you want to say B, C, or D, you got to answer this question. What's the agent? Direction. A force whose direction changes as direction of motion changes, what's the agent for that? Horizontal force, what's the agent? Force in the direction, what's the agent? There's no agent. Nothing's in contact with it. Easy. Yeah. All right. Look at this arrow. When this arrow is flying through the air, what force is exerted on the arrow? Gravity. If you want to say air resistance, if that's what's being dealt with in the problem, air resistance, but generally not. That's it. Now you say, well, something shot this arrow, right? There was some kind of, there was a bow. You had to draw the string or whatever on there and you shoot it, right? So that's a force, right? Yeah, but is that in contact? Is the bow in contact with the arrow as it flies through the air? No. No. No forces need to keep the arrow forward as it flies. Okay. Now this brings up a very good question here. No force is required to keep the arrow moving it forward as it flies. Something, got it started, but nothing's required to keep it going, So that brings us to a very interesting concept here. And in order to introduce this concept, I have a question for you. Now, do I have any astronomy people in here? Anybody take me for astronomy before? One. I recognize two. Well, Daniel, I thought you did. Salma, I can't remember if you were in astronomy or trig. But, some of you. There's a few. Anyway, I have a question for you. Why does the Earth spin on its axis? Why does the Earth spin? Why? What do you think? Look at that. Jacqueline. She remembers. Magnets? No. Go back to listening to your insane clown posse. Because it does. Guess what, people? That's it. Why does the Earth spin? Here's my official, fully accurate scientific response to that question. Because it does. Because it does. Nope, not gravity. The Earth spins because it does. That is my official physics response to you. Now, what am I talking about here? Because it does. This is Newton's first law. Now, the Earth takes 36 hours, 56 minutes, and 4.096 seconds to complete a rotation. That's how long it takes to complete a rotation. Why? Because it does. It's constant motion. And you don't have to explain constant motion. That's what Newton's first law is. Now, the technical explanation is the following. An object that is at rest will remain at rest, or an object that is moving will continue moving in a straight line at constant velocity if and only if the net force acting on the object is zero. Now, when it comes to the Earth, here's a question you can ask yourself. The relevant question is what started the motion, not what maintains the motion. Nothing is required to maintain the motion of the Earth in terms of rotation. Not even Big Bang. You would say that the initial contraction of an interstellar cloud that formed our sun and eventually formed the planets was originally spinning, and Earth inherited that spin when it formed. That's ultimately the reason why. But nothing is required to explain why it keeps going, though. Same thing with the Voyager 2 spacecraft. Launched in August of 1977. It's flying out of the solar system right now. Why? Because it's obeying Newton's first law. and it will continue to move in the direction it will move for the rest of eternity unless a net force acts on it. All right, anyway, so you don't have to explain why constant motion's taking place. You do have to explain why constant motion's not taking place, though. If sudden speeds up or slows down or changes direction, there is an explanation for that. That's really what Newton's first law is all about. Okay? You don't have to explain constant motion, but there is an explanation if the motion is not constant. There's two types of this stuff. When we talk about equilibrium, there's two types of equilibrium that we're going to discuss. So when I say constant motion, no net forces act on it, there are two situations where net force is zero. One is called a static equilibrium, and that means the velocity is zero and the acceleration is zero. Another type of equilibrium is a dynamic equilibrium, which is when your velocity is not zero, but it is constant, and the acceleration is zero. So like the example of the Earth spinning is basically dynamic equilibrium. When I say basically, it's because the Earth does slow down a little bit. There's a little bit of tidal friction from the moon and slows our rotation down by a few milliseconds per century, but that's pretty irrelevant. Okay, so this terminology here you'll hear me use quite a bit. Static, equilibrium, dynamic, and you just got to remember one is at rest, one is moving, but they're both acceleration zero. Question for you here. An object on a rope is lowered at a constant speed, which is true. Which is true. Object on a rope is lowered at constant speed, which is true. We got letters we got here. What letters, what letters, what letters? Peter McLaughlin. What? What are you talking about here? The answer here is, I need to move on a little bit here, so I'm not going to give you too much of an opportunity to guess things here. The answer here is B. If the object is lowered at a constant speed, then according to Newton's first law, F net is zero. There's only two forces that act on the object. Gravity is down and tension is up. Tension must equal gravity. Must equal gravity. Okay? I'm just going to give you the letters here because, again, I got 12 minutes or so, and I want to make sure I get through as much as I can. An object on a rope is lowered at a steadily decreased speed, which is true. The answer here, well, I mean, let me go through the logic, and then I'll show you the answer about that. Okay, so this is not constant speed. And so the question you want to ask yourself is, if it's a steadily decreasing speed, that means the acceleration is upward, right? That's what we learned about vectors before. Velocity is down, acceleration therefore is up. If acceleration is up, net force is up. Net force is up if acceleration is up. That means tension must be stronger than gravity, which is A. Hollow tubes lies flat on a table. A ball is shot through the tube. As the ball emerges from the other end, which path does it follow? Well, the reason why it curves in the tube is because it's in contact with the wall, and there's a centripetal force, which is a normal force that's being exerted on the ball. But as soon as the ball leaves the tube, there's no more force exerted on it. Now Newton's first law is at work. And at that moment that the ball reached the area where it exits out, its velocity was straight up at that moment. And so it's going to follow Newton's first law and continue to go in a straight motion. If you say A or B, then you're saying that a direction changed and there needs to be an agent to produce that acceleration. Okay. And it's not the ground or anything like that. Okay. There's no ground here. So this is all about Newton's second law. Okay. Once we identify the force, if we know the mass of the object, we can determine what its acceleration is. And that's really what all Newton's second law is about. Newton's second law is really an extension of the first law. It's an extension of the first law, and it says, well, if you do have a net force, what's going to happen? If you do have a net force, and you've worked it all out from your superposition stuff, then the magnitude of the acceleration on the object is proportional to the mass. That causes the acceleration, okay? Now, of course, acceleration is in units of meters per second squared, and mass is in kilograms, right? The product of those two is a new unit called the Newton. It's capital N for Newton, named after Sir Isaac Newton, who kind of like did some things in physics a while back. But what this says is that the acceleration of an object is directly proportional to the force on it, but modified by how much mass it has. Okay? Simple enough. But there's a lot of math behind this. I know it's a simple equation, F equals ma, but the fact that there are vectors here makes it actually a little mathematically challenging. Okay. All right, I'm doing it.
Professor, what does the M in that equation stand for?
Mass. The mass of an object in kilograms. Yeah. All right, here we go. I'm going to mention this word once and never again. When we call this mass M here, we're referring to inertial mass. Okay, inertial mass. So the best way to explain what inertia is, it's this sentence right here. The tendency of an object to resist a change in its velocity is called inertia. That's what inertia means. In no other context should this word be used. In fact, this is the only sentence that the word should ever be used, other than you're using the word inertia wrong. That's another sentence that you can use the word inertia in. There's only 2 sentences you can use the word inertia in. Actually, there's 3 sentences you can use the word inertia in, because if you're explaining how inertia is not used correctly, all right, there's probably 4 sentences now, but I'm getting this is getting out of hand. So inertia basically means that. It's the tendency of an object to resist motion. If an object has a high mass, you can't accelerate it as much for a given force. That concept is inertia. Okay? You push on a bowling ball with the same force you push on, you know, like a beach ball. Okay? Same force on both objects. You're not going to move the bowling ball as much because of its mass. And that whole concept is called inertia. Okay. Inertial mass, which happens to be equal to gravitational mass, which may sound something we easily take for granted. We don't know the answer to that question, by the way. Why is inertial mass and gravitational mass the same? We don't have a complete picture of what's going on there. So it's interesting. All right, the way you use Newton's second law, and we'll see a lot more examples of this later. Anyway, the way this is utilized is like this. You take your forces and you do the superposition, where you sum them all up. And the acceleration of the object is the F net vector divided by m. And one of the things about this is it tells you that F net and A are in the same direction, and that is true. Question for you here, don't answer it though. A cart is pulled to the right with a constant steady force. How will its acceleration graph look? Okay, if it's being pulled to the right, the velocity is to the right, and because it is force is being exerted on it, it will be accelerating. So it will be speeding up. Okay? But it's a steady force. If it's a steady force, the answer must be C. Constant force, constant acceleration. The next step after we do a force identification diagram. By the way, just real quick here, I am going to finish this lecture right now. I mean, if you want to log out at 12:20, that's your prerogative. I only got another 5 more minutes, but I don't want to keep if you don't want to be here. You can see the video later. Do I have any announcements? We don't have school tomorrow, so don't show up for lab. All right, so the next step after we draw a force identification diagram is now we can draw a free body diagram. You have to first identify all the forces that act on the object. You must draw a coordinate system with axes labeled, and then you draw your force vectors on the coordinate system. That's how you draw a free body diagram. Let me show you some examples of that. Where is that? Right here. Draw a free body diagram, FBD. I'm going to abbreviate a lot, FBD. You've just kicked a rock on the sidewalk, and now it is sliding along the concrete. Here's the force identification diagram for that. There's a rock, pretty good rock, to be honest. Draw a circle around the rock, it's in contact with the ground. I'm illustrating the velocity going to the right. Normal force is up, gravity's down. And because I said the object is moving to the right, the kinetic friction is to the left. That's the force identification diagram. When you want to do the free body diagram for the rock, you're going to draw a coordinate system. You should label X and Y, and you label them in such a way that indicates which direction is positive. If I label X over here, it's positive to the right. If I label Y up here, it's positive up. Gravity down, normal force up. Notice that the vector lengths are equal because it's not moving, it's not accelerating in the Y direction. There is a kinetic friction to the left of arbitrary length. And that is the proper free body diagram. Coordinate system, vectors drawn, properly labeled, as much as one can be correct with their lengths. Okay? Here's another example. You slammed on the brakes and your car is skidding to a stop while going 20 degrees, while going down a 20-degree hill. Free body diagram. We have a car. I draw the 20-degree hill. I circle the car. It's only in contact with the ground. Gravity's down. Normal force is perpendicular to the surface. Kinetic friction would point up the ramp. So when I want to draw a free body diagram of the car, I draw a coordinate system. I am tilting the coordinate system though, because the surface is tilted. So you do want to draw the tilted coordinate system because it's always good to make sure gravity is down. And the two other forces are along the axes. And so it will make your math easier. Remember that whatever the ramp angle is the angle that gravity will make with respect to the y-axis here. This is always true. Okay, we have a tilted coordinate system. Ramp angle is the same as this angle right here. I draw gravity straight down. I draw my normal force along the y-axis, and it should have a length that's equal to the y component of gravity here. And then I have my kinetic frictional force here, and that is a little bit longer than the x component of gravity, indicating that we are slowing down because the net acceleration is up the ramp. That is a complete free body diagram. Coordinate system, labeled, forces drawn, correct lengths, labeled. Okay, that's what we're looking at there. So you don't have to answer these questions, I'm just going to go through them. A ball has been tossed straight up. Correct free body diagram just after the ball has left the hand. Okay, so if the ball is tossed straight up and it's left the hand, then there's no contact with the ball. The answer must be D. Only gravity is involved. Only gravity is involved. Okay, you don't include the hand because the hand is no longer in contact with the ball. So you just draw a gravity vector down, and that would be the complete free body diagram. An elevator is lifted by a cable. It is moving upward and slowing. What is the correct free body diagram? So if I were to do a force identification here, the only thing that's really in contact would be the cable. So gravity's down, which they all have, and there must be a force that's upward. But it's moving upward and it's slowing down. If the velocity is upward, then the acceleration must be downward if it's slowing down, which means F net is downward, which means the answer must be C. Tension must be a little weaker than gravity because F net will be acceleration is down, and since the velocity is up, that does indicate that we are slowing down. B would be equilibrium. A would actually be accelerating upward. F is just wrong. E and B are the same, pretty much. Although E is not a free body diagram, right? And D is just doesn't make sense because there's an extra force which has no agent, so it doesn't make any sense. So it is C. A ball hangs from the ceiling by a string and is pulled back and released, which is the correct free body diagram just after its release. Okay, well, we need gravity. I see A, B, and C have gravity. D does not. D's wrong. A shows no other forces, but clearly we have a point of contact here. A is wrong. C has 3 forces and B has 2 forces. But there's only one thing in contact, and that's the string. So this third force that's down and to the right here, that's actually the net force, but you don't include that in a free body diagram. Everything you include in a free body diagram has an agent. A single force with an agent. There's no agent for this force, so the answer is B. Gravity down, tension up at an angle there.